Greetings, this is Artie from Artifact Electronics. Today we're going to have a look at this power supply unit, transformer and a rectifier board. This comes out of a 1978 Bally KISS pinball machine. It sat in a friend's garage for years and years and years on a shelf. I already vacuumed this thing in the garage because there were cobwebs all over it. But it still needs a bath. Now, there were other machines, other pinball machines that used this, but this one was clearly marked as having come out of a KISS, so that's what we're going to call it. Let's go ahead, service it, well, test it and service it as required. Here's a rectifier board itself, which you can see is still filthy. Connectors are pretty carbonized and probably will need replacing. There are two bridges mounted underneath that use the frame as a heatsink, and these contain dual diodes. Basically, two of these make up a bridge rectifier, but I guess generally this stuff is under-spec'd. And I guess originally they had 3 bridge rectifiers in them, but I guess the third one kept burning out, so they finally redesigned the board and put the heavy duty bridge in here. So that's really what it is. And of course, on the other side we have the transformer. Now this needs a bath, and this is immersible. You can wash it in a bathtub and hose it down and scrub it. This you can't. A non-hermetically sealed transformer cannot be immersed in liquid. You will ruin it. Probably cause a fireworks show if you power it up afterwards. So what we're going to have to do is separate this board from the transformer, and we'll have a look here, but you can already see that the wires are running underneath. There's no plugs. These are soldered to the underneath of that board. But let's have a look. There's 2 screws here that are holding the bridge rectifiers to the plate below, so it makes good contact with the heatsink, but I bet you there's not a trace of heat transfer paste left on this, because this thing's old and it's set for a really long time. It's held in place with these plastic spacer grippy thingies, which can be removed with the proper tool, because otherwise you'll rip these to shreds and you'll have to replace them. I think the one I have, started out its life as a popsicle stick. It was just the right diameter. So, cheap tool there. But, let's see. Yes. Oh, here's a plate that mounts under the bridges here and connects to the case. And yes, it's completely dry. There's nothing, absolutely no trace of anything left on here. And next, so the next problem we have is, you can see these wires are soldered on. I'm sure they had a good system for it, but you know, soldering directly on to traces underneath, there are holes here, but this leaves a large, or poses a large potential for soldering these wires back on incorrectly. And so we're going to have to find a way to wash this thing without getting the transformer wet, and without me having to spend 3 hours documenting where everything's connected, desoldering everything, and then putting it back together just to find out that a mistake was made. Now another option is, it's probably a little bit easier than that, is to desolder the wires that go to the transformer on both sides. These are a little bit easier to identify and document before taking them apart, but Part of engineering is to design things with economy in mind, and also to repair things with economy in mind. So we're going to come up with something so we don't have to remove the transformer. In order to do that, let's remove the transformer from the base plate. It's got 4 screws that go into threaded holes. At least I think there are. I just looked at it. And once this guy comes off, we will cook up a method to do this without getting baby wet. Alright, so this is off now, and it comes off. That way we can even clean the base plate properly. But how do we keep the transformer dry? Well, we're going to use a shower cap one, or something that simulates a shower cap. I.e., we're going to put the transformer into this big plastic bag, and then basically tape it off over here so water can't get into it. Now, it still won't let us immerse it because I'm not going to get a watertight seal over here with using tape. But if I'm careful while giving it a shower, there may be a few drops of water that get in here, but they're not going to hurt the transformer. And we're going to make sure not to immerse this, of course. So we should be fine, and we'll have this cleaned up in a jiffy. Alright, here it is. The lighting is not ideal, but hope you can still see this thing is wrapped up in plastic and has some tape. And using gravity as your friend, water isn't going to flow uphill, and at least not a lot of it. So we can hose this thing down and pay close attention. I think there's going to be a lot of dirt coming off of this thing. So let's see. And there you go. Alright, I'll get a brush and brush it off a little bit and then give it a final rinse. And for those of you cringing, PCBs, most PCBs are perfectly safe to be immersed. Keep in mind that after these things are wave soldered, they got to get rid of all that extra crap that's on the board, so they get bathed in flux remover and God knows what all. So this part's good, but again, as I mentioned, the transformer, no dice. So we're back on the bench. I set this up like this and punched a couple of holes in the bottom of the bag so any water that got in here can drain, but there really isn't a whole lot coming off. There's some water here, but that's all coming off the board. So let me remove the bag, use some compressed air on this guy, and then we can get down to business. Looks like it worked. As you can see, nary a drop made it onto the transformer. It's still got the original dirt on it, but this one looks a lot better now. And when we get down to testing it, we can actually tell what's going on and what isn't. One thing that jumps out at us right off the bat are, you can kind of see how badly burnt the connectors, I mean the headers are over here, so these are going to have to get replaced. The others cleaned off. And I'm also going to have to clean the fuse holders. Some of them are corroded and or carbonized pretty badly. And there was a repair attempt on this. Obviously this bridge was replaced, the one under there. And well, I mean, the next step is, of course, to test it. This is the bridge I'm talking about here. There's a hole burnt into the phenolic board here, and they just kind of ran out one of the legs and soldered it to a trace. And well, I got to check on that. I generally, unless something is really, really, really ugly, I don't replace it just for the sake of making it look better. This is borderline, but if it still works, I'll probably clean up a little bit around here, but I leave the bridge in there. And of course, if the bridge doesn't work, then it's academic. I then cleaned up the transformer a little bit. There was some surface rust on here, which I got off with a fine steel wool pad. If you see any marks of any rust on a transformer laminate, get rid of it, because if that progresses and gets in between the laminates inside, that will ruin the transformer. These came off pretty easily, so things hadn't traveled very far. I did straighten out the fins on the heat sinks, which need to be properly straightened out for proper heat dissipation. And what we're going to do now is replace these guys. Now beforehand, let me point out the 20-watt soldering iron is not going to hack it on these, because there's large traces and pads for these, so you got to use something a little stronger. What I found works well is this Walmart special 30-watt iron, and that's what we're going to use to desolder those connectors with. Oh, and I also removed all of the fuses, checked them for the proper rating, and cleaned up the insides of the fuse clips a little bit, so we are all making good contact. And all the fuses were good, and the values were correct. So for the desoldering, I generally don't do it on camera, but a few viewers have asked me to show the gory details, so I'll do a few pins on camera. I'm going to use the gun. And let's see. Okay, ready to go. I think I didn't let this heat up long enough. Or sometimes the pins, when the pins are too thick, it won't. So you can see this makes short. So, and you go on and on and on till all of the solder is removed. And see, yeah, it did remove the pad over here, which is to be expected. When you have a pad that isn't connected to anything, there's not enough heat sinking action on it, and usually you'll rip it off the board when you do this. So what you got to do is check every single connection once you put the new part in. I'll be back. Well, these guys fought me valiantly. I mean, they went kicking and screaming after using the desoldering gun. They still wouldn't come out. I had to use solder braid and a 30-watt iron to kind of get all the remainder of the solder, and then finally cut the plastic holders apart because they just didn't want to come out. But they're out with a minimal of board damage. Again, as I mentioned, a couple of pads got lifted, but those were single standing pads which have a connection on the other side of the board, so no biggie there. And here you go. Here are the new connectors, and I think we can finally go into the testing phase. Now, a valid question some of you may ask is, why do you go through all of this without knowing the state of the board? What is it, like catastrophically destroyed and you did all this work for nothing? My answer to that is, come on, it's a rectifier board. There's a bunch of bridges under here, some diodes, fuses, 2 resistors, and these diodes over here. And if any of these are bad, I'll replace them. And there really isn't that much board damage on here. The only damage is over here where one of the bridges kind of burnt through the board, but obviously there's still 3 good pads here, and we'll just have to use the leg to fasten it over here. So I don't see a big problem. I mean, I make the grand statement of saying this board is definitely fixable, whatever's wrong on it. And another thing is, a lot of these boards have become valuable. Actually, on this one, the transformer is the part that's valuable, because something that 20 years ago got thrown away wholesale now has become non-obtainium, and these are very special transformers. I mean, you can find places that'll rewind these for you. There are places that you send this transformer to and say, hey, make me a new one. And I guess they go in, they unwind it, and figure out the turns and everything and give you a new one. But it gets pretty expensive, at least a couple $100, if not more. So, and these transformers are pretty good. I mean, they usually don't die. Hurts me to think of how many working ones were thrown away, but anyway, it is definitely worth fixing this power supply board. Oh, another funny one here on the fuses. See if I can show that. Look at this fuse. It looks like a Venetian bridge. Looks like it saw its light flashing before its eyes because it was just about to give up. But I guess something good happened. That's a 20 amp fuse. And look at it. Look at the link inside. This is what I'm talking about, how that is bent. So yeah, it was going to bend, and then finally give up its life. But I guess the machine got turned off just in time. Does that need to be replaced? Not really. It's still good. I mean, just because the fusible link is a little bent on a fuse doesn't mean it's any weaker than it was originally. So that's going to stay in there. And one more look at these beautiful header pins here. You can just look at these and see them conducting so much better than before. So whatever gets hooked up to this is going to scream. It's probably a good idea to have a look at the schematics before testing anything, so you guys know what I'm talking about. So here's the transformer. We got AC coming in to the primary. I think these are input voltage selectors. They have different tabs on the transformer to select those. I already checked it, and it's set. It's wired for 120 volts, which is my line voltage here. We have 5 secondaries, and what they generate is from top to bottom. We have 49 volts AC going through fuse and a transient suppressor, and that goes to a bridge, and yeah, that's about it. All the negatives are tied to ground, and this outputs 43 volts DC. This also has a bleeder resistor on it, which technically isn't necessary. It's a safety thing, because what this does, if there's any capacitors down the line and you turn the system off, basically this bleeds the voltage off to ground so you don't shock yourself. Second secondary is 173 volts, which is for the gas discharge displays. The one on above it was for solenoid voltage. This one runs through a fuse, and the The bridge you see here is actually made up of 4 discrete diodes, good old 1N4004s, and generates 230 volts DC. Next one, 7.3 volts AC, not rectified, and that drives the general illumination. And yeah, should be 7.3 volts AC. We then have an input of 9.2 volts AC, and this is where those large TO3 packages come in. It's 2 of them, and each of the packages, their 3 terminal devices, have 2 diodes in them, high current diodes. And that outputs 6.5 volts DC, which are the controlled lamps. And finally we have a 12 volt AC tap that goes to the second bridge and generates 11.9 volts, which is the unregulated 5 volts, which gets regulated to 5 volts further down the line. But that pretty much sums up what's on this board. So let's get started. We're going to start with a dry test. That means we're not going to power it up. We're just going to measure components in place. And let's keep the schematic handy here. So first thing is, remember on the high voltage side they use discrete diodes, and those are located over here. This guy's obviously been replaced because it looks different than the rest. But let's see. Well, it'd probably help if we put this into diode test. And then, so we have 521 millivolts forward voltage, and that's most likely going to be different from the other 3, which are original, because they don't come from the same batch, but that one's good. 531, 577, 600. So they show quite some variance, but they're rectifying, so we're good over there. Let's do the 2 big power resistors. Let's see, this one is supposed to be, you can't read the markings on it anymore, but from the schematics I think it's a 25 ohm, and that's sitting on the 6.5 volt DC line. And this one reads 26.3, and the big guy, this is also a bleeder resistor, and the big guy is listed as 600 ohms. Close enough. And now let's have a look at the bridges under here and here, and the high current diodes. We can get this to stay, and it does. So on the diodes, this is the case. Let's see what's common on these. So the way we got to do this is measure from the case. 1 and 2 are the actual terminals. We don't want to measure resistance. Yet again, we want to measure forward voltage. 472 millivolts, 498. That one's good. And for the other one, that one's good, and that one's good. So for the bridges, we got to turn it around again because they're mounted upside down. And what we do is we go where is the positive terminal here? I think it was this, wasn't it? Well, let's find out. The negative lead goes on the positive. Nope, that's not it. This is positive. Lower right corner. So that one's good. That one's good. We then move the positive lead. I'm obscuring things, but so we put positive lead on the negative DC one and measure. That's good. And that's good. And now repeat, rinse and repeat for the second one. And finally, the hacked terminal. And that one is, oh, yes, the negative one goes on here. So everything on here checks out. So now it's time to put this guy back together again and do a wet test on it. And yes, I did get a chance to quickly clean up the base plate. I mean, I didn't use steel wool. I spent just a few minutes on it getting the surface dirt off, but it looks nice. And no, I'm not going to re-chrome this. So we're going to slap some thermal paste on it, put everything together, and continue. Now to test this, we obviously got to give it AC. And so I just made a little cable, AC cord on one side, and a connector that I just crimped the AC into. That's the way they do it. So that plugs into here. Oh yeah, and I also put a key in here, which is a well, the key is a toothpick that I stuffed in there and then cut flush. Especially since that's carrying AC, I think the key is very important. And what we're going to do, we're not just going to go and plug it in, even though we have tested things and everything looks good. We are going to use the dim bulb tester. And this is a quick way of telling whether there are any shorts in the device that you're about to power up. I did a video on this, and I'll link to it in the comments below. And that'll tell you exactly what it is. But so if we plug this in, messy desk, and move the soldering iron out of the way. So the way this thing works, very briefly, as I said, do you want details? Have a look at that video, but it's basically got an AC bulb. It's got AC coming in, an AC bulb, and then the output is this is a normal household outlet. It's plugged in and turned on, and it doesn't do anything because right now there's no path for the current. So the first thing we're going to put in to make sure that the bulb's good is put something in called a, well, I call it a dead man's plug. And that's because this is basically a big short. But what that's going to do is complete the circuit, as horrifying as it may seem to put a shorted plug into an AC outlet, but the way this is wired, it's going to make the bulb glow. And there you go. Bright bulb. It's using up all the current. So now what we're going to use it for is, instead of plugging this into the wall, we're going to plug it into the dim bulb tester. Let's turn it off first. And what this is it's a quick test of whether we have a short, an AC short, in the device under test. If there is any sort of short, what will happen? Well, you already know, because a short in this would essentially simulate the dead man's plug, and this should glow real brightly. If it's dim, and you guessed it, that's why this is called a dim bulb tester, that means there are no obvious shorts in this, and we can go ahead and plug this into a live AC outlet and start testing it. You cannot test it with the dim bulb tester because this reduces the potential to a point where all the voltages that are reaching this are off, completely off. I mean, even without shorts, something's got to light this, and since it's in series with this, so don't attempt to test anything while it's hooked up to a dim bulb tester. But here goes the test, and it is significantly dimmer than what it was before. I'm not sure if the camera really shows the difference, but yes, it is dim. This is telling me that there are no shorts in this right now, and we can go ahead, plug this in, and start measuring the output voltages at the test points. So for the voltage test, we could plug it into the wall, but to be extra careful, I'm going to plug it into the variac you see back there. And what that does for us is, unlike the it's kind of like functionality like the dim bulb tester in terms of safety, because I can turn the current, I can dial in a current limit of a few hundred millivolts over here, and if the device under test draws more than that, this guy just shuts off. And of course it's also acting as an isolation transformer, just in case I mess up and stick my fingers in there. So if we get back here, zoom out a bit, turn it on. I already got ground connected to the meter. And let's see what gives. Okay, we're sitting at 120 volts. And we start with test point 1, and looking at the schematic, that tells us it should be at 6.5 volts DC. Now keep in mind there's no load on this, so some of the voltages may be off slightly, but they shouldn't be that far off. So here goes test point 1, and we're reading DC voltage. Oh, we're not reading DC voltage. This meter, I always get confused because my other meter has one voltage setting and you select between AC and DC, but this one actually has specific settings for it. So back again, test point 1 is supposed to be 6.5 volts DC, and it is 7.6, but that'll probably drop real quickly. Anyway, this is driving, what is this driving? Test point 1, where'd test point 1 go? Oh, test point 1, 6.5 volts, which is the controlled lamp, so we're good. Next we have test point 2. That's the high voltage, that's the unregulated high voltage for the gas discharge displays. It should be, they list it as 230 volts DC, but generally it's lower than that on the rectifier board. We're getting 165. This is actually generating 180 volts DC. So when you put a smoothing cap on it, it will give the correct voltage. So that one's okay too. TP3 is 11.9 volts DC. That's what's coming out of these two big guys. That's the unregulated 5 volts, which is listed as 11.9 volts. And TP3 is over here, and that reads as 13.94. This goes through a 5 volt regulator, so this should be plenty good. Next we have test point 4, which should give us 7.3 volts AC, which is the general illumination. And I mean, it's the same kind of bulbs as in the controlled lamps, except the minute you apply power to the machine, those come on. There's no on-off switches for them or anything on these machines. So whatever, you know, bulbs, these bulbs don't care if you're driving with AC or DC. So, but we got to switch now to AC. And test point 4 gives us 7.11 volts. That's also good. And finally, we are on test point 5, which is a solenoid voltage, and we expect to see 43 volts DC on it. That one's pretty close. So, it felt like something was heating up, but I guess it was just my imagination. But anyway, yeah, the voltages are all good. I mean, a full test, of course, would include us hooking up whatever boards this feeds and seeing the boards work and all of that. But I think we did what we set out to in this one, and that was cleaning this thing up and testing it. The only repairs required were basically, yes, the headers that I replaced, a little bit of cleanup, a little bit of thermal paste, and it seems to be working just fine. So next time I'll have to dig out some boards, build some more harnesses, and see if this can actually drive, make a CPU board work reliably. Probably will, but I mean, all the voltages look good and all that, but you know, we need to put a real load on this, and that would be the final test of whether this works correctly. But enough for today. Thanks for watching. Please like, subscribe, blah blah, hit the bell. You know what to do. And leave me a comment. And we'll see you next time. Bye.